take a look at another simple but interesting situation pertaining to Pauli's system of particles and collision. What we have is a fixed pulley, and one end of the with a light inextensible ideal string passing over it, frictionless, and there is a mass 3 kgs resting on a surface, horizontal surface, and there is this free end on which there is attached a mass 1 kg. There is a particle of mass m not equal to 1 kg, and everything is at rest. The system is at rest. Now at that instant, there is a particle of mass m not equal to 1 kg moving upwards with a velocity of 10 meters per second, collides with this mass 1 kg, collides with this mass 1 kg, and sticks to it. Now, what we want to find out in this problem is that, first of all, you have to identify what's exactly going to happen subsequent to this impact. Two, for having done that, you want to be able to find the maximum height attained by this mass 3 kgs, and the instant t when it reaches the maximum height. From this instant, at what instant will it reach its maximum possible height, right? So now let's understand what's exactly happening here. First things first, when this particle collides with this mass and sticks to it, it's a perfectly inelastic collision, right? So energy is not conserved, but momentum goes nowhere. Momentum is preserved. The two masses then together move up with a velocity given by u, and the combined momentum that they have is m plus m naught. M is 1 kg, m naught is 1 kg, m plus m naught into u. U is what I want to find, the velocity of the combined mass m plus m naught right after impact. So that's u. So then m plus m naught into u, the upward linear momentum of this must be equal to the linear momentum of this 1 kg particle m naught, which is hitting this. So the total linear momentum that this brings into the system is m naught into u1. That means 1 into 10, 1 into 10, and that you divide by m plus m naught. M plus m naught is 2 kgs, so that makes it 5 meters per second. That means now, right after impact, the combined mass m plus m naught together move up with a velocity of 5 meters per second. Together move up with a velocity of 5 meters per second. Now, ordinary common sense, really ordinary common sense, and what you figure out is that if this combined mass moves up with a velocity of 5 meters per second, what would you expect would happen to the string, and what would you expect would happen to this mass? Hey, would you not want to believe that if this happens, the string here will slacken? This string will slacken, right? There is slackening of the string. This string slackens. The tension in this string will become 0. Tension in this part will become 0. Yes or no? Yes. Now what would happen? So if the tension becomes 0, this combined mass will move up solely under the influence of gravity with an initial velocity of 5 meters per second, and with gravity g acting downwards. So at some instant of time, its velocity will become 0 because g is acting downwards, right? And once that velocity becomes 0, it will start to fall down again. The string will slowly and gradually get restored to its original length when it falls again. So if this mass, having reached its maximum height, the combined mass, which is 1 plus 1, 2 kgs, with an initial velocity of 5 meters per second, reaches its maximum height where its velocity will become 0. Velocity becomes 0 because of the influence of gravity. Yes or no? And then it will come back to the same position with a downward velocity of 5 meters per second, right? Now, what's the time it takes for this complete round trip? 2u by g, twice the initial vertical velocity by g. U we've obtained from conservation of linear momentum. 2 into 5 divided by 10, that means 1 second. That means in 1 second, this combined mass will come back to this, and the string becomes taut. There is sudden build-up of tension in the string. There is impulse produced in the string. There is jerk produced in the string, right? When this mass goes up and then comes back to this position with a downward velocity of 5 meters per second, the string becomes taut. There is jerk produced in the string. If there is jerk produced in the string, what would happen to this mass? This mass will experience an upward impulse. So if this mass experiences an upward impulse, let's say subsequent to that, let's say post that impulse, the just before the impulse, this combined mass had a velocity of 5 meters per second downwards, and this mass had zero velocity before the impulse of tension or before the jerk, right? Right after the jerk, let's assume that this mass, because of the jerk, starts to move up with a velocity v naught, right? This mass, 3 kg mass, will start to move up with a velocity v naught. So obviously this has to move down with a velocity v naught. Yes or no, right? Now I can, between this state where it's just coming down with a velocity of 5 meters per second, and these two masses right after the jerk, right after the impulse of tension, will have velocities v naught and v naught as shown, right? String constraint. So if this has a velocity v naught downwards, this will have a velocity v naught downwards. And then I conserve linear momentum. I mean, linear momentum, I could straighten this portion up. If I straighten it up, it's like right after impulse, it's as if m plus m naught. Just imagine this to be straightened. Has a velocity v naught this way to the left, and this 3 kg block has a velocity v naught to the left. That means the combined linear momentum in this direction just after the impulse, right? Why is the impulse? Because this mass suddenly thumps down with a velocity 5 meters per second. The string becomes taut. And then the combined linear momentum right after the impulse is m plus m naught into 5. Yes or no? I'm sorry. It's like 2v naught plus 3v naught, which is 5v naught. 5v naught, and that must be the initial linear momentum at the instant when this is jerked, right? Just before the jerk, all that we have is m plus m naught. Imagine again this to be straightened. Just imagine this to be straightened. This has a velocity 5 meters per second just before the jerk. Just before the jerk. Imagine this to be straightened. So m plus m naught into 5. So m plus m naught into 5 is the linear momentum it has when straightened. And then right after the jerk, if I straighten it up, then m plus m naught into v naught plus 3 into v naught, and that will produce v naught equal to 2 meters per second. So then, this is a 2 kg block, this is a 3 kg block, and this has an upward velocity right after the impulse, which is v naught, which is obtained as 2 meters per second out of conservation of linear momentum. I could even write impulse equations to obtain this velocity of 2 meters per second. And having said this, this being heavy and this being light, even though they are moving in this direction, the acceleration of the 3 kg block would be a downwards, and the acceleration of the lighter block would be upwards. So both will retard. Both masses will retard. And what is the value of the acceleration? m2 minus m1 by m1 plus m2 into g, which turns out to be 2 meters per second squared. Yes or no? That turns out to be 2 meters per second squared. So this is 2 meters per second squared downwards. This is, we have found v naught as 2 meters per second upwards. And therefore, would you not want to believe that the maximum height that this 3 kg block would attain is v naught squared by 2a, twice the retardation, which turns out to be 1 meter. V naught squared by twice the retardation will be the maximum height, and the time t2 it takes is v naught by a. V naught by a means 2 by a we have obtained as 2. That means 1 second. That means the total time it takes for this mass to go up and come down, that we have found as 1 second. And then it takes another 1 second from this instant of time for this to reach a maximum height. So the total time taken is going to be t1 plus t2. That makes it 2 seconds. That makes it 2 seconds. Yes or no? So I hope you understand everything that I have communicated here in this problem, and that you are comfortable with these basic ideas. But I want to share more illustrations with you. Thank you so much.